Welcome to the HiRSE-Seminar series on research software engineering in Helmholtz and beyond.
Thank you very much, Claire. And yeah, I'd like to start my presentation with a question. Do you all know when the first numerical weather forecast was made? I'd like to take you into a little tour into the past to understand the community where we are coming from and where we are going to. So, yeah, the idea of the first of a numerical weather forecast was already raised in 1904 by Wilhelm Bjerknes. And at that time, well, the formulas were not already there and also the mathematics, or nobody could do the mathematics that fast. So then it was about 10 years later, Louis Fry Richardson had the idea, okay, I will start working on a forecast. And well, he started around 1915, but then the First World War came in between. So it took him also quite a while to do the forecast. And well, he finally published it in 2022. And well, in the end, it took him 6 weeks to calculate the change of the atmosphere over Europe within 6 hours. But it turned out that the result was quite unrealistic. Nowadays, we know it also has to do with the initial condition and the quality of the data. But already back then, he estimated that it takes about 64,000 computers as he named them, but actually it were people, or as he thought about students, um, are actually required to do a global weather forecast fast enough that it is done before the actual weather happens. So it took quite some more time until 1946 when John von Neumann suggested to use a computer to do a weather forecast. And then finally, the first weather forecast was calculated on an ENIAC machine in 1950. And then actually the developments started and took up some speed. In the 1970s, the atmospheric models were first developed. Then it turned out, well, it's not only the atmosphere, we also need the land surface to do a reliable weather forecast, which was added in the 1980s. In the 90s, of course, most of the globe is covered by ocean, so ocean and sea ice were added. Later in the 90s, people also realized it's not only atmosphere, land, ocean, sea ice, but also atmospheric constituents like sulfate aerosol, um, trace gases, other aerosol particles, clouds play an important role. And so the Earth system model built up one by one. Vegetation was added, atmospheric chemistry, and ice shields. And over the time, it was each of these compartments where a research field on its own already. And many of them also already used HPC technology. So to have a comprehensive model, one has to combine all these compartments, and this puts some demands of the Earth system science community on the model complexity, but also on the computing power. So to have everything together in a sufficiently high resolution exascale HPC systems are required. But as you can see, since atmospheric development started many decades ago, we also have quite some legacy codes in the research field. So for example, the oldest code parts I discovered during my work was some code modules from the late 1980s that still or just run on our Jewels booster system here in Jülich. I just don't name the code now. But also I came a few years ago across some Pascal modules that were switched on. So yeah, but why do we need to have all these models, these compartments, and also these high resolutions? In these pictures, you can see some of the challenges which we have today. So if we look here at the floodings of the valleys, for example, it's not only that we need to have the atmosphere simulated well, the clouds and the precipitation patterns, but also the land surface needs to be in a sufficiently high resolution to capture the terrain, the slope, and also where the runoff will happen, and to also see which impacts it has on settlements. Um, Another aspect, this picture was taken about 3 weeks ago near Jülich and Heinsberg. These thunderstorms, when they develop, they are very localized, have very detailed, lots of microphysics going on, small scale processes that need to be resolved. And just a few kilometers next to it here in Jülich, we had nearly no rain at all. And in Heinsberg, for example, there were these huge hailstones which caused some damage to cars and also houses. Um, Also, processes, for example, like these heat waves in Siberia need to be considered. So, which means this is some chemistry that needs to be resolved in this atmosphere or in this Earth system models. So, when the permafrost heats up, it melts and releases climate-relevant trace gases. Or on the other hand, we have these heat islands in cities where we need to have really high resolution. Climate relevant trace gases are a global problem. And yeah, we need actually high resolution and many processes that have to be resolved just to answer the urgent questions of our time. So in Germany, we are in the comfortable situation that we actually have a dedicated computing center for climate science and Earth system research, the Deutsche Klimarechenzentrum. So it provides not only compute resources, but also impressive storage resources and technical support to the Earth system science community. The DKRZ was founded in 1987 in Hamburg, and the main shareholders are the Max Planck Society, the City of Hamburg, and via the University of Hamburg, with some minor shareholders from the Alfred Wegener Institute for Polar and Ocean Research and the Helmholtz-Zentrum Herion. Um, well, they have, also impressive compute powers. So their Levante system is still ranked in the top 500 list, but also very remarkable. They have a storage of more than 400 petabytes, just to compare to the storage of a computing center like Jülich, which is an all-purpose centrum. They have this only dedicated for this community to store the data, the model results, and for further analysis. Yeah, speaking about Jülich, we are now in the lucky situation that we are hosting Europe's fastest supercomputer with a Jupyter booster that will be soon accessible to users. But we also have on our currently running systems a system model simulations. So it's about 15% of the compute projects on the Jewels booster come from Earth system modeling and they are in the fields of atmospheric dynamics, ocean modeling, groundwater water catchments, atmospheric chemistry, remote sensing, and geophysics. Here in the figure, it's I think the light green to the over orange to the yellowish color. So to put it in a nutshell, so Earth system modeling, the community as a long-standing and experienced HPC user. But yeah, the question is how to make the best use of the next generation of next generation HPC systems. And there is a community activity going on. There is the vision to form a German, um, yeah, Earth system modeling capability, um, entirely of codes that are mainly developed and maintained in Germany. And the idea is to create a world leading, multi scale, seamless, and ready to use Earth system modeling capability um, that serves many purposes. So it's from operational weather forecast over research, training, and also education. So this initiative was started several years ago, and it's a community-driven collaboration. So in the first place, there was a requirement for an exchange of expertise, and this initiative is also supported by the German Deutsches Klimakonsortium. Um, well, this is all unfunded activity. So there was the idea to have a funded project, the so-called natESM support team. We started in November 2021, and this project is funded by the BMFTR. So in this project, we have a project management and community coordination and 4 research software engineers that offer the community as service with sprints of up to 6 months. This is basically the core of this project. So yeah, who is the community? So the community is distributed all over Germany and consists mainly of members from Helmholtz, Max Planck, and some universities. This picture was taken at the group picture was taken at the first community workshop, and since then, more people have joined this initiative. Oh, okay. I see missing. There are University of Cologne, so people from other university also have joined during the course of the project. Yeah, but how is this community organized? So as a basis, we have this big community, and there is a steering committee which consists of representatives of the major research centers and universities here in Germany. They work on developing a strategy how to achieve the goal of a German national Earth system modeling capability. And they try to converge with the decisions on selected core components of this Earth system model. They set up working groups and also figure out which are the most relevant basic configurations that should be provided to the community. Then what I'm speaking in the remainder of this talk is mainly the natESM support team. Um, it is a project located at the DKRZ and the Research Center Jülich, where we have a coordinator and a project manager located at DKRZ and 4 research software engineers, where 2 are at the DKRZ and 2 are at the Research Center Jülich. The engineers offer a up to 6 months long sprints, and in the project also community once a year community workshop is organized, and also dedicated trainings for the community are organized to bring the latest development from computing to the system modeling community. And then as a third pillar, there are the working groups. They form from the community, and so form we had a working group on the communication platform, one on education, and now one on ice sheets models. So in the natESM team, or in the natESM project, we are working, or the coordination and the management have the very important task to work on the communication, to disseminate information, bring the community together, organize this workshop, and also provide the documentation of, let's say, lessons learned during the sprints to the community. They've set up this very nice natESM website. Then I think the most of the time is spent in the sprints, where one research software engineer teams up with the developers of the different codes. And in these sprints, different goals can be achieved. For example, one can set the goal to set up or develop a concept and set up a demonstrator for the concept. One can challenge us or ask us for an implementation of a certain aspect of the software, and also performance analysis and optimization can be subject to the sprints. And so far, I think most tasks were related to porting codes and coupling codes, as well as modularization. Then we have these trainings and workshops in the natESM support team. So far, we had 5 community workshops once a year. We have also offered already 5 trainings on selected topics, and we have some quite extensive documentation on the website about documentations on the sprints so far, lessons learned, and further documentation. Mm, One first task of the whole initiative was to get an overview about the Earth system model components that are available in German, and they are split up into core components, extended core components, infrastructure components, impact components, and optional components. So far for the German Earth system model, the icon model was picked or selected as the atmospheric model. And for ocean, there are two models selected, so either icon ocean or phasor. For land, the decision still has to be taken. As an extended core component, icon art, which allows for atmospheric chemistry simulations with in the atmosphere, was selected. And then there are the infrastructure components, YAC, which is a coupler, and COMIN, which is the community interface for ICANN, which is a standardized, defined interface where the community or the different compartments can easily um, extract data or couple with ICANN. Impact components is still on our to-do list, but we asked the community to register their codes, and they were quite active so far. 46 optional components are registered. It's from codes named AgroC to Yaxt, and they cover the atmosphere, ocean, hydrology, land, ice, vegetation, soil, chemistry, aerosol, data analysis, assimilation, and infrastructure components. Um, Yeah, one important aspect is to get some support from natESM, for example, in form of a sprint. There are two main requirements. The first one is that this model should be an open source model. This is just an overview of the licenses used for the registered components. So the majority has some open source license. There are only so far 7 codes that are not open source, and these 9 codes are either unknown or people are really working heavily on getting an open source license, which at least from some codes where I got some insight is quite challenging because they have quite a lot of legacy modules in there written by different people at times where nobody thought about licenses. The second prerequisite to have a natESM sprint is that the major software contributor should have an affiliation in Germany. So how does it work to get actually a sprint? So I would like to explain this here with the sprint timeline. So in the beginning, people who think about having a sprint, there is a very low barrier that you just write an email with a brief sprint description to the coordinator for a very quick check to see if it really fits all the conditions and timeline of the sprint. And if you get a yes or a go, you can write a full sprint proposal, which is also around, I think, 4 to 6 pages usually long. And after that, there will follow a technical evaluation by the research software engineers and a scientific evaluation by the members of the steering committee. Once you have passed this, what you can start with a sprint. You will have a kick-off meeting and start with a sprint. These are the 6 months of the sprint. In between, there will be a progress meeting, and when you have finished the sprint, you have about a month's time to write a final report. And after your sprint is done, you're usually invited to the workshop to present the sprint and your sprint results at the workshop to the broader community. Um, this process was not, how to say, fully set up at the beginning of the project. We had a rough idea, but it was refined over the time. So, for example, having the quick sprint check with a brief sprint description is quite helpful or beneficial. So, if you have a rough idea, you do not have to write a full proposal, but just can start with a brief email and then go on, or maybe make some adjustments as proposed. This is an overview over the sprints we had so far. I know it's quite a lot of text. I tried to highlight some of the topics which is about, but what I actually would like to point out is here with the models. You see, icon is quite frequently popping up here. And another code name that pops up also is messy. I will speak about this later. Um, but here I'll come to a graphic overview what the sprints so far have been about. So the majority of the sprints was about any form of GPU porting, and after that followed by coupling. Some sprints were focusing on I/O, and then we also had other sprints. One peculiarity which we have in the Earth system modeling community is the programming language. The vast majority of the codes is written in Fortran because as if you remember, as I mentioned, they already started developing atmospheric models in the 70s, and later on Fortran was the language to go for scientific codes. Um, a little fraction is C++, some C, and also some Python was the programming language used in the codes. But now I'd like to come to some sprint examples. So first, I'd like to introduce the ICAN model. It stands for icosahedral non-hydrostatic weather and climate model. This model is used for the operational weather forecast in Germany and Switzerland. And as I said before, it's also the atmospheric component of the German Earth system model. So it's has the specialty that it can span the range from weather to a climate model. It was initially developed by a consortium from the German Weather Service, the Max Planck Institute for Meteorology, the German Climate Computing Center, the KIT, and the C2SM. ICAN is a grid point model using finite differences on an icosahedral grid. That's why it also has this name. And it's pretty large code. So it has about 770,000 lines of code, mostly written in Fortran 2003. It has a hybrid parallelization. And the atmospheric part is fully ported to GPUs. Here in the sketch, you can see there is the ICAN atmosphere, which is coupled via the YAC coupler to ICAN ocean and also to the ICAN land. ICAN ocean and ICAN land are not yet fully coupled to GPUs, so there's still the work going on. And ICAN uses the YAC coupler, which is one of the two infrastructure components. I mentioned before, it uses this coupler to couple to the ocean. And since January 2024, it is also available as an open source code. The second code I pointed out in the list of the sprints we had is MESSI. MESSI is a modular Earth system, Earth submodel system, which means it's an infrastructure for coupling atmosphere models to several Earth system model components. So in MESSI, you can have, it's called a base layer. You can have an atmosphere model, a base model, for example, ICAN, that is then has an interface layer in the MESSI and then can be coupled to, currently it's 122 submodels that are available, which cover vegetation and chemistry. It also has a cloud and aerosol microphysics convection included. And one thing I would like to point out as a base model, it cannot only use these full-blown atmospheric models, but there's also the option to have a dwarf model, which is very helpful if you want to do technical developments. You do not have to go with a full-blown atmospheric model like ICAN with these nearly 800,000 lines of code, but you have this tiny dwarf that just mimics the interface, kind of. MESSI itself also has a large code base, mainly written in Fortran. And at the beginning of the natESM project, it was just a few submodels were ported to GPUs, but not yet the infrastructure. Just thinking about, coupling ICAN atmosphere ported to GPUs with a submodel ported to GPUs, you still have the interface on CPUs. So this was also the first sprint that was the MESSI team applied for, was to develop a GPU porting strategy. for their messy infrastructure to GPUs. They had a particular focus on an efficient data transfer between host and device. And for this messy dwarf, for this implementation, the messy dwarf was used instead of a full-blown atmospheric model. So in this 6-month sprint, the first implementation was achieved, and yeah, the porting of the submodels is ongoing. Here on the same slides, I also have the last sprint of MESSI, which is a MESSI import. This is one of the few sprints which were dealing with the file I/O. So there was the plan to revise the import strategy of MESSI for icon MESSI, and the idea was to develop and implement a MESSI submodel for importing and distributing gridded input data. For gridded input data and regridding, YAC is a quite useful tool, not only coupler, but is also very beneficial when it comes to regridding data. So a YAC implementation in MESSI was also foreseen. So this was the last sprint with MESSI, but in between there was another essential or two other essential MESSI sprints, the MESSI COM-in sprints. COM-in is, as I mentioned, the icon community interface. So in the picture you can see before COM-in, in MESSI one had to put entry points in the base model codes, which means with every new release of icon, one should touch icon at the entry points in icons so that they can be used together with MESSI. This is quite some repetitive and tedious work. So the idea was to have a community interface, a defined interface for the entire community that can be used, which you can see here. So icon gets this community interface. So MESSI only has to connect to the COM-in plugin or define the COM-in plugin. So whenever icon gets an update, there is no need to touch icon again. Right. During this first sprint, a prototype plugin was implemented, and in the second sprint of COM-in, this prototype or the icon MESSI setup was finalized. Another sprint example is a path flow code. It's porting a code that was already ported to GPUs to another type of GPUs. Namely, this code was first ported using CUDA to NVIDIA GPUs, and the goal was to run this code on Lumi in Finland, which has AMD GPUs. So the path flow model is a parallel watershed flow model which simulates the hydrological cycle. So basically from rain, river runoff, and groundwater or water in the soil. So it just rains just from on top the plant canopy to the bedrock. This model is quite mature. It's written in C and can be used on many platforms. It can run on a laptop and on HPC systems. And to abstract the parallelization, it uses an embedded domain-specific language approach. And maybe you know it. I think these days everybody is probably interested in groundwater. When it's hot, you just want to know, do you have to water your plants outside or not? So this it's actually used to provide this web service of this water monitor of Germany. So in this sprint, as I mentioned, Pavlov was already ported to GPUs using CUDA, and it was already also ported to GPUs using Cocos with the CUDA backend. So there is this EDSL macro for sequential call, and then this macro call for the CUDA device, and then there is this EDSL macro using CUDA with the using Cocos with the CUDA backend. And to run it on Lumi, the idea was just exchange the CUDA backend with the Cocos HIP backend. Sounds simple, but well, there were quite a few how to say, tasks to take or detours to take until this sprint could succeed. So maybe if you have already worked on Lumi, you know that you basically have to install all your software alone. This, yeah, one can never underestimate this challenge actually, installing the whole software stack so that it works. But in the end, this sprint was quite successful. And here you see the weak scaling results on Joul's Booster and on Lumi, where you have the nodes on the x-axis and the performance in cells per seconds on the y-axis. And here I would like to point you to this red line here, which is the native CUDA implementation, which is the fastest on Joul's Booster. And the green line here is the Cocos CUDA implementation, also on Joul's Booster. And the y-axis is the same on the left and right side, but if we go to the right side, we see it for Lumi. Here, just have a look at the red line, which is then the Cocos HIP implementation. So what you can see nicely, it's faster than the Cocos CUDA implementation on Joul's Booster, but all still a bit slower than the native CUDA implementation on Joul's Booster. Um, yeah, in this specific case, quite a substantial time after the sprint, so the group continued working um, on this project, and they just submitted a paper to the SC, which is currently under review, which is also a nice outcome for a software sprint, I think. And with that, I would like to close my presentation. So to summarize, the Earth system modeling community has a very long history in computing and using high performance computing systems and still has quite some legacy codes. Then there is this initiative, a bottom-up initiative from the German community to develop a national German Earth system modeling capacity. And we also found out that the sprints are well received by the community. As an outlook, maybe you noticed the project, or at least the funded project, will soon end this summer, but we have a follow-up proposal for a second line, for a second phase in line, and hope for funding. And we also have an additional machine learning component for the second phase, and also want to provide access to well-defined model configurations for ensemble climate setups, air quality setups, and high resolution setups. And with that, I'd like to thank you, and yeah, you may ask questions.
Thank you for watching our seminar. Please check out the slides on Zenodo linked below and see you next time.